Space weather!
Looking at the solar disk at 171 angstroms, we see a sunspot setting. That's 2729. And we see a likely sunspot rising. That looks a little bit too active to be anything besides a sunspot. Let's zoom in. Check out the magnetic looping. Notice some filamentary activity in 304 angstroms also. So check it out. Most of the activity on the sun today is looking like it's north of the equator. Got big time plasma filaments. Something got released up here. And we're in a coronal hole wind stream. Let's look at the magnetic lines. Now, you can see this coronal hole is finally rotating out. We're getting the wind. You can see heavy magnetic fields around this area. Strangely, the empty spots are where the fields are dense because you're looking right down the barrel of them. Now, major magnetic density on the North Polar Crown. And it looks like this smaller coronal hole is masking a bit of the magnetic field from this incoming active region. And lower density, but more heavily connected fields on the south. And let's look at the most recent earthquake activity, as we do about this time. Okay, going back about 10 hours. Japan's got a 5.0, New Caledonia a 5.1 there. Where's that one located? Colombia? Argentina. A 4.6 at depth, so they stay on alert for a 5. Russia, 4.6, 4.9, the Falkland Islands. Haven't heard of one of those for a while. New Caledonia, also a 5.0, a 4.6 in Russia. And that's your earthquake update. Let's look at the real-time solar wind, as we are in a coronal hole wind stream right now. And there's that real-time solar wind. Solar wind density 6.79 protons per cubic centimeter. The BTBZ is convergent. The phi angle is looking like a bit of a signal there, around 300 or so. And 536 kilometers per second for the elevated solar wind speed. Let's head to spaceweathernews.com. Look at the rest of the sun's details. No X-ray flux for 2 days. Wait a minute here. Alright, glad we caught that. We almost missed some data there. Haha. So actually there was a B-class flare yesterday. Probably from sunspot 2729. In fact, let's have a look. By the way, we will leave links to all of these. This is the NOAA Space Weather Enthusiast dashboard. And if you're watching this video, you're probably a space weather enthusiast. So, head down to the Solar X-ray Imager, Press play. Let that load, and there you go. There's your X-ray imager. See if we can see that flare happen. Yep, that was out of Sunspot 2729. 99% sure. And while we're here, let's look at the total electron count. Content, rather. Should be very low. And we believe the map will corroborate that data. The darker it gets, the lower it gets. A couple little spikes. Very low electron flux. Back to spaceweathernews.com. See, the magnetometer reached a little higher peak than it did previously. Very spiky. That's the sputtering connection with the coronal hole. And we expect this to smooth out as that coronal hole rotates out. The KP index is elevated to 3 due to that elevated solar wind. There's your very low electron flux. And this has not dropped off as the previous coronal hole wind streams. So keep an eye on that. That could plummet. Not sure on that one. We do have some charging hazards. Central America. Nothing too extreme though. Strange total electron count rate over the South Atlantic anomaly. A little bit of ion fountaining down there. And the F2 layer is looking pretty normal, except for this discharged area right here. Heavily discharged. So there will be a big tidal force as the sun rotates in. Let's look for that to charge up throughout the day. There's your aurora forecasts. Northern Hemisphere and Southern Hemisphere. Pretty strong auroras. Now, let's talk about the planets and orbits, etc. So we head to theplanetstoday.com as they have an animatable map. You can see where the planets will be tomorrow or an hour from now. So that's pretty cool. You can even see where they were yesterday, right? So, Earth, Venus, and Mercury are on one side. Jupiter and Saturn are on the opposing side. Mars is kind of in the night sky there. And if you're getting up before sunrise, we recommend you look to the east or southeast if you're in the northern hemisphere, or northeast if you're in the southern hemisphere, because there is a crazy Venus out and it's phasing, so it's very bright. I mean, Venus has been mistaken. Venus has actually caused train delays because a conductor saw Venus rise over the horizon and thought it was a train. So, and we would like to talk about planetary orbits. What's so interesting about planetary orbits? Well, throughout about my first 40 years of life, I thought planetary orbits were held in place simply by inertia and gravity, where these planets are just on a tightrope, and if anything pushes them out, they're going to fly off into space. If anything pushes them in, they're going to fly into the sun. And we're here to tell you that that just isn't true, because magnetic fields hold these planets in place. Let's look at how. So, we direct you again to the Primer Fields by David LaPointe. What are the Primer Fields, you ask? The Primer Fields are the dipole toroidal fields that make up the sun, and likely all matter in the universe, actually. And we're just going to play a couple tiny clips out of this video. Please don't delete our video, YouTube. So here's the plasma phase of the experiment going on. But we're going to focus on the non-electrified magnetic fields.
Magnetized and non-magnetized balls.
Now you can see these balls.
The amazing arrays shown here.
You can see these balls rotating.
The only thing holding these.
Shouldn't centrifugal force push these balls off of this piece of plexiglass? Well, nope. Because the primer fields are holding them in place. This is how the planets orbit. If the planets try to get closer to the sun,
are the magnetic fields
if the planets try to get closer to the sun will exert a pushing force on them. And if the planets try to get farther away from the sun will express a attractive force on the planets. And here's another demonstration. Of how the field strength affects other fields. Yes, folks, this is happening at the orbital level. Moving on, look at some articles. And thank you, European Space Agency, for creating a composite image of the polar North Pole. Now, many of you watching the video are probably very surprised that the North Pole of the Sun looks like this. Why does it look like this? Because this is an enduring coronal hole. And that's just the structure of the Sun. So shout out to the European Space Agency. Nice job putting that image together. The solar North Pole. We will leave links to the article. And indeed the David LaPointe videos. Now, let's look at an article in Universe Today. Oh my gosh. Greenland. Ice loss in Greenland is accelerating! And we are so sick of hearing about this. We will leave links to the article. 25 years of elevation changes caused by ice loss. Now, we know laser interferography, not interferography. We use lasers on satellites to calculate the elevation. And now you can see there's some ice loss around those areas. Even though right now, like these areas here, for instance. See these areas? The northeastern portion? Well, the thickest ice in the world is right there right now. And this does fluctuate. So, in any case, we'll leave links to that article, but let's look at the actual data from right now. So let's look at the Greenland ice mass balance. There you go. There's the ice mass budget. And there's some images. You can see there's loss in some places and gain in some other places. Now, these graphs may require a little interpretation. They're a little confusing. Look at the 27 to 2018 line. It's like a brown colored line. You can see Greenland had an extremely early fall. I mean, it was gaining ice in June of last year, and this nonsensical article is talking about how, you know, there's historically low ice in 2018. It's just not true. I mean, here's the data. It doesn't lie. And this is the same calculation that's used to write their article. because to calculate the volume, you got to get the elevation, and you're just going to assume that that's all ice there. So there you have it. And here's the fluctuations. I mean, look at the mean for 2010 through 1981. There it is. So that article is BS. We are so sick of hearing about it. Let's look at the rest of the sea ice in the Arctic, because this is freaking nonsense. And governments want to tax you. I mean, this is complete nonsense. You saw that. You saw that Greenland chart, right? See that ice right there? At the northeast corner of Greenland? That's 5 feet thick. Just kidding. It's 5 meters thick. So you've got 15 feet of ice there. Now the western portion of Greenland isn't icy. It's very thin ice there. But look at the Northwest Passage. It's looking kind of frozen, people. Let's look at another article here. Something a little less idiotic. Here's a good one, studying the magnetosphere. The NASA Magnetospheric Multi-Scale Mission. Good times. Measuring the disconnection and reconnection of magnetic field lines in plasma. Good times. Link to that article also. And last but not least, we were going to talk about China's social credit system yesterday, but we put that off. China has launched a probe to go to a location where nobody's been. No rover or lander has ever touched the far side of the moon. So, Pink Floyd will be proud. And there you have it. Thanks for watching. By the way, we don't do the videos because we hate astronomers. We do the videos because we love humans and we want to see physics rewritten because of the implications it will have on mankind. Right now, our understanding of the stars and cosmology in general is completely warped by the gaseous model of the sun. We've been using, for pushing 200 years, this gaseous model to calculate things like the age of the universe, the mass of stars, and the movement of things like stars and galaxies, and it isn't right. So thanks for watching. Stay tuned, and remember, when you're on your way to becoming an astrophysicist, don't drink. And if you drink, become an astrophysicist anyway.